On the 28th of August, 1789, William Herschel, the King's Astronomer, who had earned that unique title 8 years before by discovering the seventh planet, Uranus, observed a remarkably faint moon very close to Saturn, the second he had found that year. He made the observation through his newly constructed, state-of-the-art 40-foot telescope. Or at least he said he did. Herschel had presented his 40-foot telescope as one of the wonders of the age. He had to. His patron, King George III, had granted him £4,000 to construct it, the equivalent of about £250,000 today. The one thing he couldn't do was suggest that the investment wasn't worth it. And yet, Herschel's Cyclopean telescope had gifted him the shocking realization that it is indeed possible to be too ahead of your time. The 40-foot telescope was too sensitive to temperature change. Its half-ton mirror would warp and bend as temperatures rose and fell, and, astonishingly, was too thin to maintain its shape when placed in the frame. Modern telescopes use robotically controlled actuators to adjust for temperature, but Herschel, for all his achievements, wasn't about to beat Intel to the microchip. On top of that, the 40-foot simply took too long to set up. Starry nights aren't exactly common in southern England, and the laborious task of assembling the monster devoured precious observing time. By the time of Herschel's moon observation, the 40-foot had become a glorified tourist attraction, and Herschel did most of his stargazing with his trusty 20-footer. About the curious moons he'd found, however, Herschel could say very little. The 5 round inner moons of Saturn, which half a century later Herschel's son John would name Mimas, Enceladus, Tethys, Dione, and Rhea, were, and would continue to be, annoyingly difficult to observe. The glare of Saturn and its rings, and the moon's relative closeness to their primary, meant that even their brightness was difficult to determine, and they would remain a mystery for centuries. One of the few facts about Herschel's moon, Enceladus, which could be gleaned from it with any certainty, was that it appeared to be locked in a 2-to-1 resonance with Dione. This resonance tugs at Enceladus's orbit, preventing Saturn from easing it into a calm, circular one. This fact would eventually reveal itself as the foundation of Enceladus's entire nature. Prior to the launch of the Voyagers, expectations for Saturn's inner moons were fairly low. The Voyager team had brushed off the moons of the outer planets as, quote, dead ice balls, but by the time the team was preparing for the arrival at Saturn, the solar system had schooled them to abandon all preconceptions. The raging fires of Io and the possibly flowing waters of Europa had raised the bar for what the team expected around Saturn. As well as 2 moons that looked like they were about to blow the Voyagers up, they found moons fractured by giant chasms, moons seemingly dusted with wispy snow, moons with other moons sharing their orbits, and one moon apparently expressing an ardent devotion to Taoism. But when eyes turned toward Enceladus, expectations were not so much abandoned as ditched in the void. Enceladus was known to be a small moon, but its precise diameter had never been known, because its albedo, or relative brightness, had always been difficult to calculate. It took direct observation by the Voyagers to finally settle the matter. Enceladus was not small, it was minuscule. The moon is barely 500 kilometers across, small enough to fit into our own moon 300 times with room to spare. This also meant that it had to be very bright, or it wouldn't have been so easily observed from the ground. And indeed, Enceladus has the highest albedo of any object in the solar system, 81%, the same as fresh snow. This was no coincidence. Enceladus's density is only 1.6 times that of water, which means that it has to be composed largely of water ice, though it is still denser than Saturn's other small satellites, indicating that it must still possess a more rocky composition than they do. The inner moons of Saturn are among the smallest objects in the solar system still able to retain a spherical shape by their own gravity. It helps that they are composed of almost pure water ice, because Saturn's orbit lies in what could be called a planetary sweet spot, just warm enough for ice to retain its pliability, but not too warm for ice to exist. There are many asteroids larger than the inner moons of Saturn that are nonetheless not spherical, since they are made of less pliable rock and metal. While Proteus, Neptune's icy moon, is larger than Mimas, which is the smallest spherical object in the solar system, and composed of the same material, but is not spherical due to its far lower temperature. This goes some way toward explaining why Saturn has more round moons than any planet in the solar system. Despite its tiny size, Enceladus looked for all the universe like it had some form of active geology. The first indicator was simply its brightness. Over time, a geologically inactive world like, say, Mimas, would accumulate a coating of dark interplanetary grime, but Enceladus' surface was pristine. It was also only half cratered, as if a cosmic toddler had taken to it with an eraser, and crossed by sinuous fractures that resembled rift valleys. Carolyn Porco, the graduate student who had first identified the spokes in Saturn's rings, became convinced that Enceladus had to possess some form of ongoing geological activity, with water rising like lava from beneath the moon's surface, covering over any earlier impacts. Enceladus was also located at the thickest point in Saturn's misty E-ring, suggesting that it might be the source for its material. But no evidence of active geology was initially seen, and other scientists were skeptical. Nothing like such cryovolcanism had ever been observed in any body in the solar system, and scientists are an instinctively cautious bunch. It would be nearly a decade of further travel before Voyager 2 would eventually observe active cryovolcanism on Neptune's moon Triton, though the erupting substance was nitrogen, not water. In the years following the end of the Voyager's primary mission, Carolyn Porco promoted Enceladus as the Europa of the Saturn system, believing that Enceladus, like Jupiter's moon Europa, might be home to an ocean of liquid water, perhaps even life. The key was that resonance with Dione, which kept Enceladus' orbit in a permanent state of slight eccentricity. Rather than orbiting Saturn in a perfect circle, sometimes the moon was closer to its planet, and sometimes it was farther away. This celestial game of it, not it, meant that Enceladus was regularly tugged by Saturn's massive gravity, possibly providing energy enough to keep Enceladus' insides liquid. The same mechanism not only heats Jupiter's moon Io to the point of almost tearing it apart, but may provide its middle moon Europa with its own, much larger ocean. Surprisingly, the arrival of Cassini a quarter-century later was not, initially, the triumphant confirmation of Enceladus' majesty you would expect. In February 2005, Cassini was reoriented to observe Enceladus pass in front of a star, what astronomers call an occultation, which, it was thought, would finally reveal its gossamer geysers. It showed nothing. Neither did two close flybys of the moon in the following 2 months. And then, Cassini's magnetometer noticed something odd in Saturn's magnetic field. The plasma flow appeared bunched up in the direction of Enceladus, as if it were colliding with some invisible barrier 3 times the size of the moon itself. The team first assumed it to be some bizarrely oversized atmosphere. This led Michelle Doherty, the investigator in charge of Cassini's magnetometer, to travel from London to Pasadena and demand that the probe be sent to within 173 kilometers of Enceladus' surface. This was no idle request. It required that a portion of Cassini's finite fuel be expended to alter its course. Candy Hansen, a project scientist on Cassini's ultraviolet camera, determined to use the probe's deep dive toward Enceladus to test for a bloom with another occultation. If there was indeed any form of emission from Enceladus, then the star's light would fade gradually as it shone through the haze. If Enceladus was inert, then the star would simply wink into nothing as it passed behind the moon's limb. The occultation results showed the star fading gradually. Bingo. The erupting plumes rose to 3 times the radius of Enceladus. Scaled up to Earth, they would be brushing against GPS satellites. A quick check with a spectrograph showed that the haze was made primarily of water vapor. In a happy bonus, Cassini actually flew through a plume in its second encounter, allowing the probe's mass spectrometer to directly study the erupting material. As well as water, the spectrometer detected trace amounts of nitrogen, methane, and carbon dioxide, while the dust analyzer was able to conclusively show that Enceladus' plumes were indeed the source of Saturn's E-ring. In November, the Cassini team finally captured the image sought for 25 years. Enceladus' ephemeral plumes caught in the light of the sun. The image would become the icon of the Cassini mission. The geysers on Enceladus did not cease erupting throughout Cassini's entire 13-year mission, and recent work on Voyager images suggests that the craft may have caught them from a distance even back then. Models suggest that the E-ring is unstable on timescales over 100,000 years, so to exist, it must be constantly replenished. This would suggest that Enceladus must have been erupting continuously for a similar period. The geysers were erupting from Enceladus' south pole, and originated in 4 parallel, claw-like tectonic fractures that the Cassini team dubbed the Tiger Stripes because their coarse-grained icy makeup made them appear darker than their surroundings in natural color. In near-infrared, or ultraviolet, the stripes appeared a brilliant aquamarine. This crystalline, coarse-grained structure suggests that the stripes cannot be more than a few hundred years old, since otherwise the ice would have melted into everyday amorphous ice. This clashes somewhat with the continuous nature of the geysers, but then these do not have to be the first vents to have formed. The stripes were found to be a comparatively toasty 190 kelvins, or minus 83 degrees Celsius, indicating that they must be channeling heat from below. Uniquely for the surface of Enceladus, the stripes were also found to contain carbon compounds. One hypothesis for the existence of the stripes, proposed by J.K. Kraft et al. Of Johns Hopkins University, suggests that Enceladus was struck by a large impactor at some point in the last 100 million years, which drove straight through the crust into the ocean. When the moon refroze, it kept the tiger stripes, which tidal stresses from Saturn kept open. Tidal force was considered to be the most likely source of Enceladus' geological activity. Obviously, it was too small for the driver of Earth's geology, radioactive decay, to play a role, at least not for more than a tiny fraction of its life. But calculations suggested that Saturn wasn't tugging Enceladus hard enough. But, as noted in my end-of-the-year list, last year a new model was formulated that envisioned the moon's core not as a solid lump, but as a grinding mass of broken grains. The friction from these grains as tidal stresses drove them against each other would generate more than enough heat to power Enceladus' geological activity for billions of years. In the 2005 pass, Cassini found that the amount of water in Enceladus' plumes suggested that they originated in a pool of liquid relatively close to the surface. This was catnip for astrobiologists, because it meant that a potential habitat for life existed within physical reach of a future probe, rather than buried under kilometers of ice, as Europa's ocean was. The plumes contained a high proportion of salt, suggesting a salty subsurface ocean similar to our own. Initially, it was believed that the ocean was really just a pond confined to beneath Enceladus' south pole, but gravimetric data, which measures the density of subsurface features, suggested that Enceladus' ocean, like Europa's, was global. Detailed observations of Enceladus' orbital wobble, or libration, suggest that its surface is decoupled from its interior, providing yet more evidence for a liquid ocean. The ocean is believed to lie under 20 to 40 kilometers of ice, though only 3 kilometers at the plumes, and maybe as much as 10 kilometers deep, almost as deep as Earth's deepest trenches. Given Enceladus' tiny gravity, however, the pressure is likely far less than we would experience at similar depths on Earth. And last year, analysis of data taken by Cassini as it passed through a plume in 2015 revealed the presence of hydrogen. So, you might argue, hydrogen is the commonest substance in the universe, except that it is very reactive and is almost never found in its purest state when there are other elements for it to bond with. The only way that the plume could contain hydrogen is if there was a constantly replenishing source at Enceladus' core, which can only mean volcanism. Heat from the core causes water to react with the crust, which in turn causes it to oxidize and release hydrogen. Hydrogen, as I outlined several times earlier in this series, is a common source of energy for extremophile life forms on Earth, which often congregate around volcanic vents in the lightless depths of our ocean. Enceladus, on paper at least, is looking like the perfect home for extraterrestrial life. There was a bit of a catch, though. Some models suggested that the salt in Enceladus' ocean would grant it a pH of between 11 and 12, akin to household ammonia or soapy water. Of course, life can adapt to such conditions, but it's better if it doesn't have to. And there's another problem. Nearly all moons, including our own, move gradually away from their planets as they age. Models of the tidal evolution of the inner small moons of Saturn suggest that they have not moved very far since their formation, which indicates that they could not have formed all that long ago. In fact, some models suggest that the moons might be as young as 100 million years, which would make them younger than birds. If that is the case, even if Enceladus' ocean had every necessary ingredient for life, it would likely still be utterly barren. 100 million years is not a long time for life to form. This hypothesis does, however, clash with crater count data, which suggests that, with the exception of Enceladus, whose active geology obscures its age, the mid-sized moons of Saturn are all as old as the solar system itself. Enceladus may have hogged the limelight among Saturn's 6 mid-range moons, but it wasn't the only one to fan the ardor of astrobiologists. Dione, Enceladus's resonant partner, is also believed to possess an underground ocean. The same resonance that induces Enceladus's eccentricity affects Dione to a lesser extent, producing similar tidal effects from Saturn. When the Voyagers passed by Dione in their run through the Saturnian system, they imaged what came to be called wispy terrain, which was initially taken to be some form of cryovolcanic deposit. Cassini showed that the terrain was in fact gigantic ice cliffs formed by tectonic fractures in its surface. These features showed signs of having been flexed in the past, an early indication of a fluid interior. Also, in 2013, Cassini's magnetometer made a contact similar to that which it had made over Enceladus 8 years earlier, a weak stream of particles emanating from the moon that resembled a more tenuous version of Enceladus's plumes. And then, finally, in 2016, gravitational mapping data pretty much clinched it. But if this is the case, what about Mimas? Aside from looking vaguely like, well, no moon, the innermost of Saturn's round moons is decidedly unremarkable. And yet, its eccentricity is higher than Enceladus, and it is closer to Saturn. It should be an aquatic Io, ceaselessly tormented by roiling ice volcanoes, not a dead lump of snow covered in craters and grunge. Incidentally, that crater, is the largest relative to its parent body for any round object in the solar system, and is appropriately named Herschel. So what happened? Well, oddly, it appears that tidal heating doesn't just happen on its own. To be tidally heated, an object has to be warm enough already to overcome its own material strength. And Mimas just never got hot enough. Enceladus had enough radiological materials at its core to keep it hot for about 10 times longer, enough to get the engine running. But Mimas was too small. Oh, and if you thought Mimas could mimic only one turn of the 80s pop cultural icon, you'd be wrong. This thermal image, which also appears on Saturn's other known moon, Tethys, is believed to be caused by bombardment of high-energy electrons, which alters the structure of the icy surface and causes it to hold on to heat stronger than its surroundings. The outer realms of Saturn's moons are not immune to the chaos found farther in. They are as much a part of the same complex dance as the spiraling moons that shape its rings. Both Tethys and Dione are flanked by 2 attending moons called Trojans, that lead and trail their orbits in what are referred to as their L4 and L5 points. A Trojan is an artifact of a queer quirk of gravity. When 2 bodies gravitationally intersect, they produce what might be called gravitational dead zones, called Lagrange points, that follow the smaller object as it orbits the larger. Anything that falls into a Lagrange point will remain locked in that position relative to the orbiting body. The largest Lagrange points, called L4 and L5, are where objects are most likely to be caught. Jupiter has a whole panoply of asteroids at its L4 and L5 points, while NASA is planning to place the James Webb Space Telescope at Earth's L2 point. But perhaps the most astonishing example of the ice dance that is the Saturnian system was tentatively detected by Cassini in 2009. Voyager 1 had noticed that Saturn's magnetic field exhibited a marked depletion in trapped electrons in the region downwind of Rhea, the largest of Saturn's moons, not named Titan. This was confirmed by Cassini, which noted 3 separate drops in plasma density. Models suggested the most likely reason was that it was being absorbed by a triple ring of solid particles in orbit around the moon. Rhea, moon of the solar system's Lord of the Rings, might have a ring system of its own. In 2009, the first indirect physical evidence for a ring was identified in a series of ultraviolet bright spots along Rhea's equator, which may be impact sites of fallen debris from the rings. Long exposure images, similar to those used to image the rings of Neptune, fail to locate any ring, but models suggest that such a ring would remain stable around Rhea over astronomical timescales, unlike moons closer to Saturn. Given the busy nature of the region around Saturn, there are any number of ideas concerning where our solar system's only known lunar system might have come from capture of impact debris to a small moonlet caught in Rhea's gravity. We will likely need another probe to learn more. There is one moon among Saturn's icy retinue that I haven't mentioned yet, partly because it is something of an eccentric misfit in the Saturnian system, and partly because, I have to admit, it kind of freaks me out. Iapetus's oddness was noted even by its discoverers. Giovanni Cassini discovered Iapetus in 1671. In 1672, he noticed that, against all logic, the moon appeared to be rising and falling in brightness at a regular rate. Since this could not be due to it moving away from the sun, he concluded that, quote, "One part of his surface is not so capable of reflecting to us the light of the sun which make it visible as the other part is." He was correct. One side of Iapetus is indeed far darker than the other. Its piebald surface enabled William Herschel to determine that, like our moon and, as would eventually be learned, every other large moon in the solar system, Iapetus orbited Saturn with one face permanently facing its planet. The voyagers were able to confirm that Iapetus's yin-yang coloration was physical. Indeed, they found that one side was as dark as coal, while the other was as bright as snow. Cassini showed that the dark patch on Iapetus was due not to a difference in composition, but to a foot-deep covering of reddish dust. Its cause is now believed to be tied to the same fact noted by William Herschel all those years ago, that Iapetus only shows one face towards Saturn. Iapetus is a distant outlier in the Saturnian system, the farthest of its regular satellites, and also the least regular. For reasons unknown, its orbit is tilted a full 7 degrees. This remoteness grants it a particularly long orbital period, 79 days, which allows its day side to be warmed by sunlight, while its night side is left to freeze. As such, Iapetus experiences a greater difference in temperature between its day and night sides than any of the large moons of Saturn. Scientists believe that at some point in the distant past, the day side of Iapetus was struck by a comet-like body, which left a black stain on its surface. The dark patch retained more heat from the sun, as dark patches do, causing the ice around it to sublimate, whereupon it traveled as gas to the night side and froze to the surface again. As ice sublimated, it left behind more dust, which in turn retained more heat, causing more ice to sublimate and more to collect on the other side. This chain reaction ultimately produced the wild dichotomy seen today. But it is not Iapetus's odd color scheme that I find unnerving, nor its aloof, frigid orbit, out in Saturn's darkest wilds, but rather what Cassini observed on its surface in 2007. I don't know what tenebrous being possessed the Cassini team member who took that shot, but to me it looks like the tomb of some eldritch astral deity, waiting for the cosmos to align and portend its coming resurrection. To top it off, no one knows why it's there. The ridge runs 1,300 kilometers along Iapetus's equator, and at 20 kilometers high, gives the moon the appearance of a giant walnut. The alien, not quite faces that line its peaks are carved by meteorite impacts, suggesting that it is ancient. Richard Hoagland, of Face on Mars fame, suggested it was evidence that Iapetus was a giant spaceship. Now, don't get me wrong, that would be cool, but ridge equals spaceship is not a leap I am prepared to make at the moment. Of the more sane hypotheses, 4 stand out. First, that it is some kind of cryovolcanic or tectonic feature akin to the Mid-Atlantic Ridge. Another is that it is a fossil of an earlier time, when Iapetus was spinning far more rapidly than today, causing it to flatten out in the middle. Over time, Saturn's gravity eased it into a far slower rotation. A third possibility is that it was the remains of a ring system that impacted on the surface. There are a number of far smaller moons in the Saturn system that appear to have suffered a similar fate. However, Iapetus is too far away from the traffic of the inner system for this to be likely. A fourth possibility is that it may be an artifact of uneven differentiation early in Iapetus's formation. As if that wasn't Lovecraftian enough, studies of Cassini data have suggested that Iapetus may be home to landslides that flow uphill, likely due to friction partially melting the slick, icy surface. And that, finally, is the Saturn system covered. I can tell you I am relieved to be moving on to the next chapter of this story, in which I will definitely be looking at the solar system's true water planets, and their equally icy retinue. I hope my first attempt at a full musical accompaniment wasn't too much of an intrusion. I spent several days trying to work out the difference between too loud and too soft. I'd like to thank one of my viewers, Janet Person, as well as Purple Planet, and of course, William Herschel, for supplying the music. If you enjoyed this video, please like, subscribe, all that good stuff, or hit me up on social media. I have links in the description. Stay starry-eyed, fellow seekers.